Welcome back, friends. Right now, we're starting talking about a very important concept in calculus called continuity. So first of all, we need to talk about continuity has three components to it. And what this is it's basically a test. And so there's these three components that we test. And if all of them are true, then we can say that the function is continuous at a point or over an interval. And then we need to be able to use that idea of continuity to be able to say, can we do other processes with the function? So let's talk about this for a minute. And so there's three parts, like I said. So the first part is this, that the function, a value of the function has to exist at the point we're talking about. So in other words, it has to be defined there. So if I plug in x, I get a value out. So that's the first rule, that you have to have a y value for the function at your point you're talking about. The next part, part 2, says that if I take the limit as x approaches that value of the function, that exists too. So let me go back here. And do you see that there's a hole right here in this function? So in this function, we would say that it is not continuous here. And I think you can see that there's a hole right there, so it's not continuous. Sometimes, I know when I was younger, I thought of continuity as being smooth. So if it's smooth and it's connected, then smooth and connected have some different meanings in math, but you know what I'm talking about. There's a hole right there. So no, it doesn't exist right there, so it's not continuous. Back to part 2, that the limit exists. And notice, super important, my dear friends, this is a two-sided limit. So yeah, the one-sided limits can exist, but the two-sided limit has to exist. So in this case, notice as I'm approaching a from one side and I'm approaching a from a different side, it's not, the two-sided limit doesn't exist. However, does this pass the first case, the first part? Is the function defined at a? Yeah, right there, it's defined. However, it doesn't pass the second part. The two-sided limit does not exist. And then, of course, the third part is simply that part 1 and part 2 have to be the same value. That's all it means. And we can write it like this, that f at a, if you pick your value a, we want to know, is this function continuous at some point a? I can pick the value of the function there, and that has to equal the limit as x goes to a of the function. And if all three parts are true, then we say the function is continuous at a. Don't say the function is continuous everywhere, because that's not what that means. We're only testing it at a certain point. Now, you can certainly test it at more points, and then we can make different claims. But right now, we're just talking about being continuous at a certain point. So let's look at some of these examples, and we'll do our test here. We'll see what's going on. We'll see how this works. So here's a function here, and here's a, and there's the point there. So is this function, this curve, is the value of the function defined at x equals a? And the answer is yes. That's part 1, so it passes that. And you can see it's all connected here and smooth. What is the limit as we approach a from both sides? Well, it's the same thing. It heads to the same point. And that means that part 3 is true, that the value of the function and the limit of the function are going to the same place. Visually, you can see what I was talking about before. That is this all smooth and connected. There's no jumps, there's no gaps, there's nothing here. It's all smooth and connected at a. The point's running right through a. That is continuous at a. So let's look at our some discontinuous examples. So in this case, here's our, this is called a removable discontinuity, and we need to know these names because we're going to be asked to classify discontinuities. The first one is a removable discontinuity where there is a gap there. The point is defined here. So I just want you to notice that is f at a, does it exist? Yeah, it's right there, but it's not where the limit is. So in this case, the limit exists and the point exists, but they're not equal. So that's called a removable discontinuity, like someone removed it. Or you could remove it and put it back, right? So that's a removable discontinuity. This one here is called a jump discontinuity where the ends don't match up. So in this case, it is defined. So it meets condition 1, part 1. There's the point right there. However, it fails on part 2 because that two-sided limit does not exist. All right. And one more example. So we have removable discontinuities, we have jump discontinuities, and then we have infinite discontinuities where we have vertical asymptotes. So in this case, this fails the first case because the point is not defined at A, so it doesn't matter. It also has no limit, so this fails like all over the place. This is a complete, and you can see, is this connected? Is it smooth? No, of course it's not connected and smooth. So those are the three kinds of discontinuities. All right, friends, we're going to add a little bit of a piece onto the continuity here. It's called the Intermediate Value Theorem. This will have more use to us later on, but right now I'm just introducing it to you. So I'll show you a picture of this in a minute. It's a little complicated when we read the words, but it'll make sense to you when you see the picture. We abbreviated this IVT, so you can just say the IVT. And there's a couple of rules that we have to follow with the IVT. Number one is that when we're talking, whatever function we're talking about, it must be continuous. That's the first rule. And it has to be over a closed interval. If it's over an open interval, the IVT does not apply. So it has to be a closed interval. And basically what we're saying is if you pick some value, some letter, in this case I'm calling it letter C, that's between the y values of, so f of the y value evaluated at A and the y value evaluated at B. So f at A and f at B. If you pick a value in there, then there's some number x that f at x has to equal that, meaning it just means it has to cross there. So let me show you a picture. It'll be simpler than my my bad explanation here. So here's our curve. So notice it's smooth and continuous here, and we're including the ends because that's the rule. Right? It has to be continuous, check. Has to have a closed interval here, check. And so from A to B, this is continuous. And this value here, this is f at A, right? And then this value is f at B here. And so what we're saying, the intermediate value theorem says, if you pick some number in between, some y value in between there, and we're picking C, that in order to get from here to there over a continuous thing, it has to cross this at least once. And this is horrible. I should have drawn this higher. I apologize for that. But you can draw this anywhere you want. The point is, because it's continuous, it has to cross it at least once. Now, could it be looping back and forth? Yeah, you can cross it all sorts of times, but it must cross once. So meaning that there's some value x. Let me redraw this there. So we're not looking at that line there. We're looking at this line. So there has to be some value x that I can plug into my function that will get me this value, that this exists, right? You're picking the c, meaning that there's an x that I can select that'll get me that c, that will find that intermediate value, whatever value you're looking for. I guess a good way to think of it is if you want to think of like driving, where you say if I'm at a stoplight and I'm going 0, and then I'm going to speed up to, let's say, 50 miles an hour, that at some point between the time you're stopped at the stoplight going 0 and the time you're going 50, at some point you have to cross a speed in between there. So for example, there is a point at which you are going exactly 20 miles an hour. There's another point that you're going exactly 40 miles an hour, because I can't go from stopped to 50 miles an hour without going 10 miles an hour at some point on my speedometer, right? Because those values are smooth and connected. You're not just going to instantaneously go 50 miles an hour. You can't do that. That would be infinite acceleration, and unfortunately our cars don't do that.